So this was about the wire feeding process in the three processes. Now the next question, how is plasma cladding and TIG cladding similar? Okay, we just talked about this, we'll still discuss more. Now, plasma cladding and TIG cladding. This also uses a non-consumable tungsten electrode. Now this also uses a non-consumable tungsten electrode. So the first, now inert gas is only used for shielding. Bead height can be increased significantly. Now in plasma cladding, as we said, the shielding gas, this is not for TIG cladding, not for TIG cladding, only for plasma. This is for both. So when this shielding gas is divided into two parts, into the inner core and here this is into outer core. This is for shielding purpose and this is for ionization and establishing the arc. Now if we can visualize, suppose consider this is the plasma. From here we get the plasma gas and this is the plasma, this is the plasma gas and we have here a separate shielding gas. Now plasma is more popular in wire additive manufacturing as compared to TIG, because here the tungsten is not projected outside and hence the bead height can be increased significantly. This is only for plasma. Okay. Next question. Which of these are correct for reverse polarity in DC arc welding? Wire additive manufacturing, this has AC machines and DC machines. Wire additive manufacturing is for AC machines and DC machines. So direct current and this is for now the straight polarity, reverse polarity. More details also we will explain further also. We have so this is easy for visualization. So here we will understand what is about the DC straight polarity, DC reverse polarity. Okay. consider this as your workpiece. Now, when the height is more, it will be a straight polarity, and here when it is less, it will be reverse polarity. So, straight polarity we use when thickness of the sheet we want to weld is more. Okay, now consider this as a bead. In 3D printing, consider this as a bead, as you can see. Okay, now the height of the when the height of the bead is more, it is straight polarity. As you can see here, when the height is less, it is a reverse polarity. Now, in straight polarity, what happens is your 70% of the heat generated is due to the input current, which acts on the workpiece. Current which acts on the workpiece. And the rest 30% is released to the tool or other environmental factors. Or to environment. Now, in FDM process, this is opposite. In reverse polarity, this is opposite. That is 30% is on the workpiece and 70% is released to the tool. Now, in alternating current, there is no polarity. So, we will get a bead like this. So, there is nothing to differentiate. It is a cyclic process. It is a cyclic process. Okay. Now, I need to just draw this. This is the bead, height more, height less, reverse polarity, this is straight. Now, so everything depends on the thickness of the sheet we want to weld. Now, when in your selective laser melting, your layer thickness is very less. So this is sometimes it is not possible. And in your FDM, your layer thickness is somewhere around 100 to 200 micrometer. So this is possible. Okay. So this was about the polarity. Now in this question, it is asked that which of these are correct for reverse polarity and DC arc welding. More heat is required for at the workpiece side. No. Less heat is required. Correct. Polarity can be reversed by making the workpiece as negative. That is correct. And workpiece can be made as anode, liberating large heat near it. So, in reverse polarity, less heat is required at the workpiece side. Workpiece can be made as negative and less heat is required on the substrate. Now here more heat is required at the workpiece side. Workpiece can be made as anode and large heat is released near it. So these are the major difference between your direct current and direct polarity and reverse polarity. Or rather you can also say straight polarity and reverse polarity. Now the next question. What happens when the residual stress is more than ultimate tensile strength of the material in wire-based additive manufacturing process? Residual stress is the remaining stress in the part after the removal of all the external forces. Okay. Residual stress, remaining stress in the part after removal of all the external forces. Okay, so we have a similar concept here also in the later questions. After understanding this, we'll come back to this question. Now, consider this as your stress strain curve. Yield stress and later you have the ultimate tensile strength. Okay. Now consider this as the UTS, ultimate tensile strength, and we'll here consider only a single, not upper yield point, lower yield point. You're only under take consideration into a single yield stress. This is the stress strain curve. Now, so what happens? Okay, so this is the question, and we are finding out what will happen if the residual stress is more than ultimate tensile strength of the material in wire-based additive manufacturing method. So now consider your residual stress is around, when it is more, suppose this is 500 and this is 400. So after ultimate tensile, after the specimen reaches its ultimate tensile strength, it will finally lead to fracture or it will break. Now that means if the residual stress is more than the ultimate tensile strength, so it has crossed the fracture limit. It has crossed the fracture limit and we will see a crack. Okay. Now, when the yield stress is, the residual stress is more than the yield stress, but the residual stress is less than ultimate tensile strength. Suppose this is 300, 350, and this is 400. So what will happen here is a permanent deformation will occur. Occurs. Now, this phenomena is mostly, like suppose this is your build plate or substrate and this is your material or specimen. Now, when this condition occurs, what happens? You will see that the material is like this. Okay, so in the edges warping occurs due to this permanent deformation. That is, the residual stress is less than your ultimate tensile strength but greater than the yield stress. And this is very usual in FDM process, specifically in ABS material. So we should always avoid warping. So according to the question, what happens when the residual stress is more than the ultimate tensile strength? So simple, crack will occur. Okay. So related to this question, we'll again discuss. Okay, this is just a common question related to data oriented, like which deposition method is most suitable for pulsed wire additive manufacturing process, and the correct answer is pulsed metal transfer. Now, I'll go through little bit on this. We'll come back to this question after discussing some other important things. Okay. So in MIG welding or cladding process, because the previous question was related to another question, so we'll come back to it. Okay. So in MIG welding or cladding process, how is the wire feed in synergy with the welding current? Now, the wire speed is in meter per minute. This is the current, and the relation is linear. The wire feed is linear with respect to your welding current. The option is linear. Okay. The question is, how is the geometric or metallurgical properties of the fused layers related to the direction of movement of the fusion source in the XY plane? So, what does omnidirectional means? Directional means equal sensitivity of the process in all directions. Now, this is various different methods. Principles of different methods of obtaining omnidirectionality. So, first is coaxial feedstock and fusion source. Coaxial feedstock and fusion source. This means your feedstock is along this here. This is BT. I'll just draw and later come and explain. Now next is coaxial fusion source and surrounded by feedstock. This is the fusion source. This is the feedstock. Next is same coaxial now feedstock which is surrounded by fusion source. And the last one is dynamically adjusting feedstock. Adjust the feedstock. That means this is the fusion source. This is your feedstock. So these are the different methods for. So our question is, how is the geometric properties of the fused layers related to the direction of movement of fusion source in the xy plane? So here we can clearly see that it is independent of the geometry of the fused layers is independent to the direction of movement of fusion source in the xy plane. So now an omnidirectional it can receive or send equally signals equally in all directions. So in omnidirectional additive manufacturing process, the geometric or metallurgical properties of the fused layers are independent to the direction of the movement of fusion source in the xy plane. Now in the first case we have this, whatever we are seeing, this is the top view. Okay, suppose this is the, for this the coaxial feedstock and fusion source. If this is the VW, VW will be VW and okay. Fine. So this is the fusion source and here it is surrounded by, and your, this is, see here, if we go to the front view, this is the fusion source and here will be your feedstock or VW and this will be your fusion stock. Now for this case, the this is your velocity of the feedstock and this will be your fusion source. This is the front view. So it is coaxial along a single axis. Now here this is coaxial fusion source, but it is surrounded by the feedstock. As you can see, it is surrounded by the feedstock. Now in this, in the next one, coaxial feedstock and surrounded by fusion source. Here we can see the fusion source is this one and this is your velocity of the feedstock. Now this is coaxial feedstock and surrounded by, now this was coaxial fusion source, but this is coaxial feedstock and surrounded by fusion source. And finally, here we can adjust, the feedstock can be rotated, feedstock rotation can be done along this direction. Okay, so the next question. What type of defects are likely to occur in MIG process when a layer is deposited on a substrate which was not cleaned properly? Now earlier we discussed about warpage. Now when here, when a layer is not cleaned properly, substrate is not cleaned properly, we will face porosities. Porosities means it will have low mechanical properties and fatigue life. So raw material induced porosity happens due to surface contamination. Raw material induced porosity, this is due to surface contamination. And process induced porosity, this will lead to poor path planning or unstable process. And result of porosity is low mechanical properties and less fatigue life. Okay, so the next question. Okay, we'll now come to discuss about the MIG-based numerical on MIG-based wire additive manufacturing process. I'll just pause the session here for 2 minutes. Okay, so we'll resume the session. So this is a numerical on metal AM. Now consider this a bead. So here the question is asking that a single bead experiment was performed on a flat substrate and a circular profile of the bead cross section was obtained as shown in figure. So find out the height of the thin wall after deposition of the 15 layers with same process parameters. So I think this is a question similar to your assignment question. I may have changed some values. Okay, so consider this as the first bead, and this bead we are considering it as hemisphere or uh, semicircle. Okay, now if this is your base plate or substrate, as you see. Now it is saying to find the height of the thin wall after deposition of the 15 layers. So see, you have been given the height of one layer, it is 1 mm H1, but that doesn't mean that this will be the height for each layers. Now we have to calculate the subsequent 14 layers of height. What will be? This is your dia 2 mm. Now so we have the formula as we know from the lecture notes, from the videos, that theta 1, this is the theta 1 sine inverse 4 h1 w1 by 4 h1 square plus w1 square. Now first step is we are calculating the theta 1. So we will put the value of h1 and w1. The w1 is 2 mm, h1 is 1 mm. So it will be sine inverse 4 into 1 into 2 by 4, 1 square plus 2 square. Now this will become sine inverse 8 by 8. This will become sine inverse 1, and in short it will be pi by 2. Or if we took in 1.751 radian. This is your theta 1. Now also we will see the ratio of W by H is equal to here 2 by 1 is equal to 2. This is the ratio. Now we need this theta 1, theta n. Theta n. Now for getting theta n, we have the formula sine theta n cos theta n minus theta n is equal to half of theta 1, which we just solved and found out, cos theta 1 minus pi. Now this will be half theta 1. See here this is in radian I had converted it, in theta terms it is pi by 2. Pi by 2 minus sine pi by 2 cos pi by 2 minus pi gets cancelled. This is minus pi. Now we have theta n minus sine theta n cos theta n is equal to pi by 4. Okay, I just missed here 4. Pi by 4. Now we have to, question is how we have to solve this equation. How we will solve it? So now from the graph here we see x is equal to sin x cos x. So that means from here we can relate it, x minus sine 2x by 2 minus pi is equal to pi by 4. Now we use the graph to calculate, we use this graph to calculate. We use graph to solve the equation. Now we will see where it meets here, this point. We will draw a straight line as you could see, and the intersection point with the curve, that will be your point, intersection point. So we will take the value of this intersection point and we will find. Now x minus sine 2 pi by x is equal to pi by 4. Here for x at 0.785, which we get. So for x at 0.785 we get the value 1.16. So this I have considered some approximations by making LHS is equal to RHS and found out the theta n value. This is 1.16 value. This is your theta n. Now this is in, if we convert it into radian, we'll get 1.16 into 180 by pi. This will be in radian. Now Hn is equal to 2r cos theta n. This will be 2 into r is your 1 into cos 1.16. This will be 0.79 mm. Now this is Hn. H1 was 1 mm. So total height 1 plus 14 into 0.79 is equal to 12.18 mm. This is your final answer. So thing is, it's not necessary that you will be always given this graph. So when you are not given this graph, so you're obviously, when you find out your x value which is here given, okay, 7.785, so that will vary according to your graph. And suppose in some case when you are not given the graph, in that point we will ask you to use this ratio W by H. Okay. Now we have next is we have to discuss single track experiment, and polarity we discussed. Cold metal transfer, this is very important, we'll again discuss this also. Residual stress we discussed, and finally we'll discuss a question on MIG welding based arc. So this is about single track experiment. This is related to the previous question which is having a single bead. Now single track experiment, when we do, we follow all these parameters: process stability, powder layer thickness, printing speed, size of the bead, wire feed rate, etc. So we will discuss one by one on all this. Now, so there are metallurgical people who are also working with 3D print. So they mostly do this type of experiments where everything is already optimized. So we don't have to do this type of experiment. This is about what I am saying is this is about the previous question where you have to find out the layer heights and everything. Nowadays that is not. We don't need to find the layer height because that is already optimized. Uh, but earlier in 2010 or 2005, we can see a lot of paper having the single track experiment. A single track experiment, these are the few things which they found using this experiments. Now we are using the same set of parameters for a commercial 3D printer, where most of the companies will not allow to change the parameters. But suppose if you want to do some new designs or new integrate structures, then we can't work on these parameters. We have to change, else we cannot. The default or the range within these which these parameters have been given, that is not sufficient for printing our specimens. Okay, so next first is we'll go to for the powder layer thickness. Now in powder layer thickness, suppose we have ALSI. I think many people would have heard this. So here printing an aluminium is very difficult. So we add a alloy silicon to it so that it can be easily printed. Now this is in the size of average layer thickness will be around 30 micrometers. Uh, Again we have like TI6AL4B where the average thickness is 50 micrometer. This will be, these are some applications which I am saying you. Now this is the substrate and this is a single track. Okay, now single tracks comes from a single bit where we can calculate the stability of the process rather than the power current. So whatever I am going to, for a single bead, so that powder thickness, okay, for aluminium suppose or ALSI 10 mg, it is very difficult to print. So we are putting a silicon to reduce the reflectivity of the aluminium. So here we have using the alloy to print. Similarly, as I said, this is again for the case of TI6AL4V. Now, um, if you see a powder like particle size, that will come in a range like of 10 to 12 micron, 10 to 20 micron, then that should be lower than the layer thickness. This powder particle size should be lower than the layer thickness which I am using. So that means I am using aluminium 3D printing and powder particle should be less than 30 micron, and it is not possible to maintain a 30 micron thickness for uh, okay, for titanium. Suppose I am using this parameter from this. Now we have to calculate this optimal thickness. How to reach finding this optimal thickness? Now we have to build a whole product. So that is it. We have to vary each of these parameters, the feed rate, the size of the bead, whether this is this much, or this much, the printing speed in the initially we can keep it as low, then in gradually increase, and again in the final we can reach it to take it to a maximum minimum level. So this all is required for the perfect finishing of the specimen as well as the mechanical properties. Okay. Next, we will understand about cold metal transfer additive manufacturing process. So, I have here given you this 4 stages, showed you the 4 stages for the cold metal transfer additive manufacturing process, and which is also in our video lectures, but we will not find this graph. So, this graph is taken from a research paper and it relates each stage of the metal transfer with the current and time graph. Okay, so first stage is where we initiate the arc and filler material is moving towards the, here the filler material is moving towards the substrate. Now here you will see a sharp increase in current in this first stage. Okay, current increases. Now in the second stage we are extending the wire towards the molten pool. Molten pool, the wire dips in molten pool, arc will extinguish resulting in short circuit and the current, that is why here you see the current decreases. Now your third stage will be retract the wire. This is 1, 2, 3, 4. Retract the wire. Here retraction will help to detachment of the droplet. And fourth stage is when the wire is retracted to default position, again same process will again repeat. Okay. So when current is less, strength is good. This is the overall schematic of the cold metal transfer additive manufacturing process, with where we see the graph of current with respect to time. Yes, so fourth one is when wire is retracted to default position, again same process will repeat. So this was about cold metal transfer additive manufacturing. Okay, so the subsequent question we already discussed about residual stress. Now we will move to another numerical where we have been given the deposition rate. It is a MIG welding based wire arc additive manufacturing process. The process parameters are given like torch speed, bead height, penetration depth, wire diameter, welding current, wire feed rate, material density, efficiency. So here it is asking the deposition rate in gram per minute. Now the formula of the deposition rate is equal to area of the bead into velocity of the wire into density. AW for area of the bead, velocity of the dW into density. Now area of the bead is equal to pi by 4 into dia is given, wire diameter 1 mm, will convert into meter 1 and 10 to the power minus 3 square into velocity of wire feed rate. It is given 8000 mm per minute, will convert it into meter, it will be 8. Then we have density, it is given 8 gram per cc, so here it will make it into kg, and meter it is 18 10 to the power 6. So this will become around 16 pi gram per minute. This is your answer. Deposition. Now next question is, what will be the bead width in mm if the bead cross section profile above the substrate is found to be a symmetric parabola? So it is saying is this it doesn't look like symmetric, but it's symmetric. Okay, consider this a symmetric parabola. So this is the optimal step over. This is for a width of a bead. Here we are taking 2 beads. Now W is equal to 3 pi VW dW square by 8 HVT. T is your torch speed, dw diameter of the wire, V is the velocity of the wire. Now this will be, we'll put all the values from the given data. W is your here 8000 into diameter is 1. Now here we are again considering in mm, and 8 into h is 3 into 500. It is given bead height 3 and torch speed is given 500 mm per minute. Now when we this is around 2 pi. Now next is asked for optimal step over. Now for optimal step over we have is equal to energy required to melt wire plus sorry this is P is equal to 2 by 3 W, 2 by 3 into 2 pi is equal to 4 pi by 3. So these are the this is the solution for. Now one more thing is, if we are asked for power, so when we are asked for power, that will be energy required to melt wire plus energy required for melting substrate. This I will say you because I haven't don't have a numerical for this. I will just explain. Melting substrate. Okay, this we have to understand. Energy required to melt wire. This again consists of two components. Okay, where you have a specific and heat and latent energy. So its formula will be somewhat AP density, velocity of wire, area of the wire, VW, specific heat, Tm minus T naught plus latent heat. Okay, so these are the two components. Now energy required for melting substrate is, this is required when the build plate is heated. Okay, now in case of metal additive manufacturing, this value is considered, but in case of polymer or FDM processes, this value is very less, because suppose your base plate is 110 or 40, depends on your material you are using. So this will only impact the bottom layer. Okay, the top layers, they won't be impacted by the energy required for melting substrate, but the in metal additive manufacturing this will get impacted. Now energy required for melting substrate this will be rho APVT. AP is the area of penetration and I'll just draw it. One second, I'll just complete the formula. Tm minus T naught plus L. Okay. So here the temperature is in Kelvin and Cp unit is joule per kg degree Celsius. So this will be constant. You can't change this. This temperature is in Kelvin. Now what is penetration? This is the height. So below this much is the penetration. This is the area of penetration, and this is the width. This is the energy required for melting substrate. When energy required to melt wire, this will be density. Suppose in mild steel, the density will be 8000 kg per meter cube. This will be pi by 4 d square. This will be the velocity of the wire. Cp will be 450 joule per kg degree Celsius, and we can consider this in 1800, and this will be room temperature, which is around 300 Kelvin, and latent heat is 5000 joule per kg. Okay. So this was all about today's class.